Hi, welcome to this video on gas laws. In this video, we're going to talk about a lot of our experimental laws. So we're going to start out with Boyle's Law. So Boyle's Law is one of our, I think, most famous, like the biggest known experimental law because it's one that's very easy to see. We see it happen all the time around us. Boyle's Law, or Boyle, was actually known as the father of chemistry. Robert Boyle, and basically his law was that the volume of a confined gas is inversely proportional to the pressure exerted on the gas. So one thing to know is all gases are going to behave like this. And so we're going to get a little more into this. So Robert Boyle was an Irish chemist, and he was studying specifically, when he was studying, was the pressure-volume relationships in gases. So he was looking at how pressure and volume were affected. So remember, when you do an experiment, you can only change one variable, and then you look for the response that that one variable or that one change had. So you've got your one independent variable and your one dependent variable. So you only study two variables at a time, and you hold everything else constant to ensure that you get an experiment that isn't tainted by other variables or other things that could be possibly happening. So Robert Boyle spent a lot of time studying pressure and volume relationships. So that means that he was really keeping the quantity of gas the same, which would mean that at constant quantity, he had to have a closed container, and he was keeping temperature constant. So he wanted the kinetic energy of the gas molecules to remain the same, because we know that you increase your temperature, you heat them up, you speed them up, they're going to end up colliding with the container more, that kind of scenario. We've talked about that previously. So when Robert Boyle was studying just pressure and volume, he found that they had an inversely proportional relationship. That means that when volume goes up, the pressure is going down. So notice, in order for volume to change, your container must be variable. So when we're in lab, so the container must be able to, I don't know what I just did there, but somehow I can't write above that, must be variable volume. That's important. So basically, when we're in lab, if we were studying this, the variable volume container we would be able to use would be like a balloon, right? But it has to just basically be something that could change overall size. And so you can see down here in the picture in this molecular view, they're using something where as the pressure goes up or down, we can see that the overall size or that bar is moving. But basically what he saw was that for a given quantity of gas at constant temperature, the product of pressure and volume is always going to be constant. And so from there, he came up with what we call Boyle's Law. So that is Boyle's Law, which was what is in italics. But the P1V1 equals P2V2 equation is the easiest form of Boyle's Law that we know that allows us to do calculations. So for example, we can change the conditions. We can start with a known set of conditions and of pressure and volume, and we can change the pressure of it and find out what the new volume should be, or vice versa. So it allows us to predict what the gas is going to do based on our known knowledge of the gas. So Boyle's Law has been tested for over 3 centuries, and it holds true at low pressures. So keep in mind, if your pressure gets too high, then you have the problem of the possibility of condensing of the gases. So you wouldn't be able to check that or use that at higher pressures, at really high pressures. Most of the time, gas molecules are going to be at low pressure anyways. All right, so over here on the right, we can see the graphical representation of Boyle's Law. So basically, as pressure increases, my volume goes up. So what we can see here is, as we go this way, right, we see that pressure is increasing. And as you go that way, you also see volume is getting smaller. Not a lot at that point, but starting initially, right? So when my pressure goes up, my volume goes down, or vice versa. If volume goes up here, like we're seeing going up, right? Then we can see when volume goes up, the pressure must be going down. So Boyle's law will always have this curvature nature of the graphical representation in lab. So if we looked at different gases and changed the pressure or the volumes, we're going to see this holds true no matter what. Again, at low pressures. All right, so let's look at the exercise number 3. So in this exercise, we're going to do a quick calculation on here. So it says sulfur dioxide, a gas that plays a central role in the formation of acid rain, is found in the exhaust of automobiles and power plants. We consider a 1.5 liter sample of gaseous SO2. So that's a volume because that's in liters, right? And that gaseous sample is at a pressure of 5.6 times 10 to the third pascals. So there's my pressure. And it says if the pressure is changed. So I have an initial set. So that's 1, or you can use initial, however you want to do it, of volume and temperature or pressure conditions. And then what we do is we change it. So now all of a sudden here's the new pressure. And we want to know, what's that new volume going to be, assuming constant temperature, and we would also assume that they would be keeping, in the scenario, keeping the moles of the gas or the quantity of gas constant. So Boyle's law, when I only have pressure and volume and I keep the temperature constant, is P1 V1 equals P2 V2. So all we're really doing with gas laws, which is nice, is algebra. And algebra is pretty simple, so we're just going to plug in what we have. So pressure 1, we have 5.6 times 10. I don't know why my pen's not working very good. Times 10 to the third pascals. And we're going to multiply that by my volume, which is 1.53 liters. And then that's going to equal the new pressure, or what it's changed to, which is 1.5 times 10 to the fourth. Again, having issues with my pen. Pascals. And we're looking for volume 2. So then we're just doing the algebra, dividing the 1.5. I'm not going to show you the algebra on all these problems, but I will show you on a couple of them just because I think it helps for you guys to see. Now, one thing that is important when you are doing this is everything has to be in the same units, because if it's not in the same units, the units won't cancel. So when they cancel out, we should be left with the volume unit, which is what we wanted here. So with sig figs, we always go with our fewest number. So my volume, the new volume, is going to end up being 0.57 liters with 2 sig figs. So that should make sense because we can easily see that our pressure went up, right? So we want to double check and make sure, does this fit with what we think should happen? So pressure went up, so therefore volume should have gone down because they're inversely related. Well, it did go down by a third, 2/3, probably about 2/3. All right, so Boyle's law is relating the pressure and volume, and it's one of our most used laws because a lot of times we are studying pressure-volume relationships with constant temperatures. Like in a classroom, we're not really changing the temperature very often kind of scenario. All right, next we have Charles's law. Charles' law is when a given quantity of gas is held at constant pressure. So we're keeping pressure the same. Then we know that the volume is directly proportional to the absolute temperature. Notice this really important. We brought it up earlier, but I'm bringing it up again. Your temperature has to be in Kelvin. That's because we're using, with Kelvin, we're talking about kinetic energy. So Kelvin is used to measure the average kinetic energy of particles. So that's supposed to be AV. AVG. So the average kinetic energy of particles is what that is measuring. So Kelvin scale is specifically for kinetic energy. Celsius was developed off of that as like a nicer scale to use. But Kelvin is our main scale of real. It's the actual SI unit that we should be using. So Jacques Charles, or Charles, was a French physicist, and the first person to fill a hot air balloon with hydrogen gas, and he made the first solo hot air balloon flight. That's because of his study with kinetic and with volume and temperature. So he was able to basically use the heat and the gas within his hot air balloon. He was able to heat it and to keep the volume of the hot air balloon full so that it would continue to float. So that was kind of how his premise worked. So basically what you'll see is volume is directly related. So it gives us a straight line plot. This little symbol right here that you see, that's a direction, like a lot of times that's used for a direct proportionality. So that means directly proportional. So that means if one goes up, the other goes up. So if my temperature increases, my volume goes up or increases. So if I increase the temperature of the gas molecules, then they're going to expand and fill the container as long as the container, again, is expandable. Anytime we're talking about changing volume, it has to be an expandable container. Otherwise, you're changing pressures instead, and we'll get to that in a minute. The plot of this graph is going to be a straight line. So if you look over here at this picture, you can easily see. So Charles' law says as temperature increases, your volume increases. So what we see happening, right, is as we go this way, my temperature goes up. And obviously, we also see at the same time that the volume of the sample of gas is increasing, or the container that the gas is in is increasing. And notice that this is the case. So you can see a difference in the slopes. These, the slope differences here are showing, so the slope differences between those four lines are because they're using different quantities of gas, but keeping them at the same pressure. So they are changing the quantity. So more gas is obviously going to take up more space, right? Because you're going to have more gas than whatever. So it's bringing that in a little bit. So the slope differences, note those are due to the different quantities of gas. But either way, we see that upward straight line slope happening. All right. So our easiest way, I don't really like this. I don't really like you can do V1 T1 equals V2 T2, but that's so confusing to me. So I remember it as, and I'll write it over here on the right, V1 over T1 equals V2 over T2. I don't really care how you remember it, but I'll explain to you, I'll show you why later I prefer this method or this version of it. But it's the same, that the one up there on the left is just the one where they've obviously done cross multiplying to make them all one line. I don't think it matters to me. So I also like to see when they're lined up like this, because when they're lined up like this, I can easily see, well, if volume goes up, temperature has to go up so that this will stay the same, right? If that doesn't stay the same, then your proportionality doesn't work. So this shows when you see two things in a formula that are on top and bottom, you know that they're directly related to each other like that. So I like that. That shows, that means more to me than what the previous one up there is. So the biggest thing is your temperature and volume are at constant pressure. So that's, you have to have a variable container to have constant pressure. Otherwise, there would be that the container, when it gets bigger, will keep the number of collisions the same. So that's how it keeps constant pressure. This figure shows the plot of the volume versus temperature in Celsius, which is directly proportional to the temperature in Kelvin, so it didn't matter. And then it goes through kind of the background of some of the things I already said. Solid lines represent experimental measurements. The dashed lines are the extrapolation, how they're going. They're able to say, well, we know these specific things. So the dotted lines is extrapolating or going off of what the actual graph is, and basically looking at the trend as a whole. The samples of the various gases contain different numbers of moles, so that's why you're seeing those 3 different samples or whatever that I was pointing out a little bit ago. One thing to notice is this right here. what is the temperature when the volume extrapolates to 0? So when we have no volume, this is a theoretical quantity because obviously no volume would mean that gas does not exist. But really, that temperature is called absolute zero. So that should sound somewhat familiar. Absolute zero is a theoretical quantity. It's never been achieved because at that point, all kinetic motion would stop, right? All kinetic motion is done. And so everything has some kinetic motion in, so therefore this is a theoretical value. But absolute zero is 273.15 degrees Celsius or 0 Kelvin. So that's why we like the Kelvin scale. It makes that number a little nicer. So, negative 273, sorry. 273 Celsius would be super hot. So at 0 Kelvin, all kinetic motion would have ceased. All right, let's look at a calculation. Okay, so Charles' law says a sample of gas at 15 degrees Celsius. So this is really important. Anytime you see a Celsius temperature, add 273. So we add 273 to that. That's going to be 288 Kelvin because we cannot plug in Celsius. It changes the values of the numbers. And so it's going to give you wrong answers if you plug in the Kelvin temperature or the Celsius temperatures instead of the Kelvins. And then, so that's your temperature, right? So it's giving me a temperature. And it says it's at 1 atm, has a volume of, so there's volume. And then it wants to know what's going to be the volume of the gas at 38 degrees Celsius. So again, add 273. So when we add 273 to that, we get 311 Kelvin. And so that's going to be temperature 2. And so from there, we're basically trying to find what is volume 2, what is the new volume, right? So V1 over T1 equals V2 over T2. So when we plug in, right, we're going to plug in those kelvins. So it'd be 2.58 liters over T1, which we said was 288 Kelvin, equals V2, we do not know, over 311 Kelvin. So in this scenario, this is why I'm showing you the math, just to kind of help those of you that aren't as good at math, is you're going to do a cross multiplication. So we're going to cross multiply. So we're going to do 2.58 liters times 311 Kelvin. That's where they got the V1 T2 is equal to V2 times 288 Kelvin, because we did the cross multiplication of this side. And then you would divide by 288 Kelvin on both sides. Hopefully you're seeing how I'm getting that. Kelvins are going to cancel. So when you plug in your volume or new volume at the higher temperature should be larger. So hopefully you get, with 3 sig figs, 2.79 liters. Is that larger than what I started with? Yes. So therefore, I can be pretty confident that that's a correct answer. So remember, they're directly proportional. So if temperature goes up, the volume should go up as well. All right, so that is looking at just comparing volume and temperature. Here's a little quick picture. This is something that I would probably show you in lab. So each of the balloons below contain the same number of particles in the gaseous phase. So basically they pumped them with the same quantity of gas, right? And then they close the balloon. So we have, let's say, I'm just going to make up a quantity, but let's say they both have 1 mole of gas, right? So we'll say 1 mole of, what kind of gas? We'll just say 1 mole of air. So it's a mixture, but that still, it won't matter. So 1 mole of air, right? And so this is an example of heat them up and speed them up, right? So if I heat them, like ice water is cold, right? So that's going to be a low temperature, which is why they're saying low kinetic energy over there. And then you got boiling water, which hopefully you realize is hot. So that's going to have a high temperature. And So, or high kinetic energy. So what do you notice happen when you put it in the cold? What we see happen is that the molecules are going to slow down. And so when they have lower kinetic energy, they have less molecular motion. So that means they're going to basically have less collisions with that container. So that volume has to shrink to keep the pressure the same. So the whole purpose is to maintain constant pressure. So it decreases volume so that it can basically keep the pressure equivalent to what it was initially. As the molecules are warming up, though, they're going to gain more kinetic energy, and then they're going to move faster, and they're going to collide more with the walls of their container. So rather than increasing pressure with those collisions, the balloon will expand, so it'll keep the pressure constant, and the volume of the container will get bigger. So that's why you see the expansion there. So low temperature, we see a shrinking or a smaller volume. But when we see the high temperature, we see an increase in volume. Now the key in both of these is the balloon or the container is expanding or contracting to keep pressure constant, keep the number of collisions of the gas molecules the same. All right, then we have, switching pages on here. Okay, almost, we're getting there. All right, so in this page, we have Gay-Lussac's law. So Gay-Lussac's law of combining volumes is the only two variables we haven't really discussed yet. And so basically it's combining volumes. Let me change colors here. So Gay-Lussac's law says that the volumes of gases will always combine with another one in the ratio of small whole numbers as long as volumes are measured at the same temperature and pressure. So basically what he's saying is at a constant volume, right, pressure and temperature of your gases are going to be directly related. So if I have, I don't know, I can add, those are, the gases are additive, right? The volumes of your gases would be additive as long as they're measured at the same temperature and the same pressure. But really, Gay-Lussac spent a lot of time studying pressure and temperature of gases. So he said the pressure and the temperature must be directly related if, and here's the difference. So this was kind of like an expansion or like an offset of what Charles' law said. If my pressure goes up and the container is not expandable. So this is what he saw happening. If your container cannot flex and maintain a constant pressure, then your container, the number of gas collisions are going to increase. So again, it was kind of the same idea. I don't really like this P1 over P1 T1. I use the same, they're directly related, so it's P1 over T1 to me is equal to P2 over T2. So they're directly related. So if I increase the temperature of my gas, if you look over here on the plot, so if temperature is going up, right, if I increase my temperature, then we can see that should make sense. You've got more kinetic energy of your molecules. More kinetic energy of your molecules is then going to increase the kinetic energy, which is then going to increase your number of collisions. And if I have more collisions, I have greater force. So that's going to increase the pressure within the container because your container can't expand to maintain pressure. So that's where pressure starts increasing drastically. So this would be like in a soda can. So if I left a balloon in the car in August, it would expand. If I left a soda can in the car in August, it doesn't have the ability to expand. So it's just going to build up pressure inside the can, if that makes sense. So it would work, the problems would work the same way, except you would be keeping temperature or volume constant in that case, and it would be a closed container still. Avogadro's law kind of is an offshoot of Gay-Lussac's law. So, or his statement up here. So Gay-Lussac's statement, I feel like that's kind of in the wrong way, but he basically said you can combine volumes of gases, right? As long as they're at the same temperature, same pressure, you can just, if I have one gas and another gas, I can just add them up and that would be double the volume or whatever. So Avogadro's law is from Amedeo Avogadro. So this is one of his important things. in addition to Avogadro's number, obviously. But his big contribution was with gases, which is where Avogadro's law came from, or Avogadro's number came from. He was contributing with gases because he found out that the volume of a gas at a certain temperature and pressure is directly proportional to the quantity of gas you have. So he said that if you increase your amount of gas, so if we increase moles of gas, then obviously my volume should go up. There's more gas, there should be more space taken up, right? And vice versa. So he said those were directly proportional as long as you're at constant temperature and pressure. So if I have 4 moles of gas, I can actually combine those volumes together as long as they're all at the same temperature and pressure or whatever. So Avogadro's hypothesis says that equal volumes of gases under the same conditions have equal numbers of molecules. That's really what he said. So remember that it's really equal numbers of moles, right? But we're going to say molecules because we know that 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules, right? So since we already know Avogadro's number is like a nicer way, mole is a nicer way of writing Avogadro's number, they're kind of go hand in hand. So if we have volume, equal volumes of gases are going to have the same number of moles, then they would have the same number of molecules as well. Like, obviously, it should make sense. So here's just kind of another picture, a depiction of Avogadro's law. Again, it's a direct relationship. So when we look at that relationship, we see that as my moles, we increase my moles, what we just said earlier should happen is we see that the volume of the container is going to increase. So there's more gas in there. That the volume has to expand to make up the difference for that. And it doesn't matter what kind of gas it is because there's large spaces amongst the gas molecules. So it doesn't matter if it's in this, that's what this picture on the right is showing. If it's N2 or H2 or argon or CH4, if they are at the same conditions of temperature and pressure, then the volumes, if they have equal volumes, in this case it's showing pictures of the balloons being equal volumes, then they must be equal moles or quantity, right? And it says this below it, these balloons each hold 1 liter of gas at 25 degrees Celsius and 1 atm. So then each balloon has 0.041 moles of gas, or 2.5 times 10 to the 22nd gas molecules. So it's really easy to figure that out. So if we wanted to know how many particles were in each balloon, right, we could easily figure that out because how many particles are in each balloon? Well, the conditions of the balloon are the same, right? So the conditions are the same. So if the conditions are the same, then what would we do? They have 0.041 moles each, right? And it's just generic moles of gas. So we can do a quick conversion, and that's how they got that number. 1 mole of gas is equivalent to 6.02 times 10 to the 23rd. I'm going to say particles of gas because it's atoms or molecules. And when we multiply those together, we should get 2.5 times 10 to the 22nd gas molecules. So each of those balloons has the same quantity of gas because they're at the same temperature and pressure, and they have the same volumes. So as long as they have the same volumes, we know that's going to be the case. So that's essentially all of our variables. So if we go over to the next, there is an actual problem for Avogadro's law, right? So exercise 6 says, suppose we have 12.2 liter sample that contains 0.5 moles of oxygen gas at a pressure of 1 atm and a temperature of 25 degrees Celsius. If all of this oxygen were converted to ozone at the same temperature and pressure, what would be the volume of the ozone? Okay, so this one's a little bit more complicated. It makes us think about a little bit about reactions. We haven't spent a lot of time on them yet, but we will. But let's think about, this is a very easy one. We're taking O2 gas and we're converting it to O3 gas. And hopefully you remember from first year chemistry that these don't match up in law of conservation of mass. So we would need coefficients to make that match up. So I'm going to need 3 O2s for every 2 ozones that I make, right? So pretty easy. So that is my mole ratio right there. So if I know the moles of one, I can find the moles of the other. That's the only reason you need that. So when we look at this, it says, suppose we have 12.2 liters. So there's our volume. And we have this many moles of O2, right? So there's my N. And it says at a pressure of 1 atm and a temperature of 25. If all the ozone is converted to, or the oxygen is converted to ozone at the same temperature and pressure. So notice same temperature and pressure. So this is just a direct relationship. What would be the volume of the ozone? So we want the new volume 2, right? And so these are directly related as well. So my volume 1 over N1 equals volume 2 over N2. That's the relationship. It's the same one we just did with volume and temperature with Charles' law. We're just switching out, keeping temperature constant and changing the amount of gas. So we can plug into that. But before we can do that, we have to do a conversion to figure out how many moles of ozone I have, because I want that other volume. So if I have 0.50 moles of O2, so we got to do a little quick conversion here. Moles of one, we can find moles of the other. So it's using a little stoichiometry, little preface. We're going to do this soon. So moles of O2 are up. So 3 moles of O2 come down, and 2 moles of ozone are going to go up. So we're going to basically take 0.5 times 2, which is 1, divide that by 3, and we should get 0.33 moles of ozone, right? So logically, okay. So it should make sense because we have less ozone. So we should have a lower quantity moles because we converted most of the oxygen into ozone. So we have less moles of ozone at the end. So when we go to plug in, I'm going to switch colors so you can see it a little better. We go to plug in, my initial volume is 12.2 liters, right? And that's for the 0.50 moles of O2. But we converted that moles of O2 to ozone, so now it's something different. So some of those oxygens have been consumed. So we should see a decrease in the volume because we have less moles of gas when this happens. So the new volume 2 over 0.33 moles of ozone, when I do the math, like cross multiply divide, my new volume, obviously we talked about, should be less than what we started with. So we started with 12.2. When you do the math on this, you should get 8.1 liters. Hopefully you did your algebra right. Which should make sense because if you decrease the moles of gas within the container, then you should see the volume of the container should get smaller as long as obviously it's expandable. All right. So last thing is I'm not going to do any calculations on this because it's, again, just more algebra. But I wanted to talk a little bit about the combined gas law. So experimentally, we would never use the combined gas law. But in real life, we never really change one variable at a time and keep the other constant. Like sometimes pressure and temperature is changing. So for example, if I accidentally let go of a balloon outside and that balloon was a helium balloon and it started to raise up in the atmosphere, my pressure's going down, my temperature's going down. So what does that do to the volume of the balloon? Because there's multiple variables changing. So the combined gas law combines mathematically all of these experimental laws that we just previously talked about. So it's combined, that's why it's called that. But it's really nice. You can use it for multiple variables changing at one time. But you can also use it as a way to determine what the laws are, what the mathematical laws are. So that way you don't have to memorize every single one individually. So for example, if we know that Boyle's law is a relationship between pressure and volume, but we don't remember exactly what it is, right? We know the other variables in Boyle's law would be held constant. So we would keep moles and temperature constant, and then what would be left would be Boyle's law, right? Which would be the P1V1 equals P2V2. Same scenario. Let's say that it was Charles' law, right? And I was working a problem, and I can see in the problem, I might not know that it was Charles' law, but in the problem, it was talking about volume and temperature changing, but pressure and amount of gas was staying the same. So it was a variable container or something. So we would eliminate out pressure and moles, right, on the equation, and then we would have our Charles law equation. So you can eliminate out any variable that is constant out of the combined gas law. So then you only have to memorize one law instead of all four that I just showed you. This will make your life a little easier. All right. So work on, that is something to be working on. I'm going to take that off. The memorization of this law, I think it is on your formula chart, but don't hold me to it. I always forget what's on there and what's not on there. And then you can always like derive any of the other four experimental laws that we talked about. So we will do a little experimental activity, either an online simulation, or we'll do something in class to practice a little bit more with these and be able to see some of these experimentally. But if you have any questions, bring them to class. Hopefully you don't. This is pretty simple first year chem stuff. And then we're going to start getting into some of the other stuff coming up.